Welcome to the deep dive. Today, we're really venturing into the fascinating, sometimes kind of surprising world of cryptography.
We are, and our guide for this is a book you shared with us, Crypto Dictionary, 500 Tasty Tidbits for the Curious Cryptographer by Jean-Philippe Aumasson.
Yeah, great little book. Our goal, like always, is to pull out those key cryptographic ideas, those nuggets of knowledge that might just shift how you see the digital world.
And the stories, too. There's some really captivating stories hidden in there. We want to give you a solid understanding, but, without getting totally lost in the weeds.
Definitely. And this dictionary, it really hammers home just how huge cryptography is. I mean, the author reckons it covers maybe 75% of the field.
Which is incredible when you think about it. It's way more than just, basic encryption.
Oh, yeah. Think about terms maybe you haven't bumped into, like CECPQ or EKMS, fuzzy extractors, the M-hash function.
Exactly. Shows the depth, right?
Totally.
And what's cool about the dictionary format is how approachable it is. These aren't supposed to be like dry academic papers.
No, not at all.
They're tasty tidbits, little bites of crypto info that hopefully stick with you.
Okay, let's unpack some of this. We rely so much on our phones, right? Yeah. So let's start there, how they keep our calls and data secure. The dictionary gets into the evolution, starting with A51.
Right, A51. That was the default for GSM phones in Western countries before we got 3G and 4G.
Okay.
And what's interesting is its design. It was kind of unusual. It's a stream cipher, generates a key stream, but it uses 3 linear feedback shift registers, LFSRs.
Okay, LFSRs.
Yeah, but the tricky part was how they were clocked. Irregularly. Imagine like 3 gears turning, but how fast one turns depends on where the others are. It's a bit more complex, but that's the gist.
Huh, sounds fiddly. And it only had a 64-bit state.
Yep, 64 bits.
Which, I mean, with today's computers, that doesn't sound like much of a barrier, does it?
You're absolutely right. Yeah, while there were some, let's say, more theoretical attacks, the way it was actually broken in practice was, well, relatively simple, a time-memory trade-off.
Ah, the classic trade-off.
Yeah, exactly. Using pre-computed tables, huge ones called rainbow tables, attackers could crack that 64-bit state much faster than you'd think.
So it highlights that need for longer keys as computing power grows.
Absolutely. A51 was, well, maybe more of a speed bump than a real wall.
Thankfully, things moved on. The dictionary mentions A53 as the next step.
Yeah.
What was the big deal there?
A53 was a really important shift, actually. Instead of sticking with a sort of secret proprietary design, which might have hidden flaws.
Right, like A51 presumably did.
Possibly. A53 adopted a public, well-vetted algorithm, the Kasumi block cipher. This was standard, already checked out by the crypto community. It ran alongside A51 and 2G, then kind of became A54 and 3G.
And A54 was even better, more secure.
Yeah, A54 was basically A53, but they doubled the key size to 128 bits.
Okay.
That jumped from 64 to 128 bits. Huge difference in resisting attacks.
So the big takeaway here is that clear move from those early, kind of shaky, proprietary mobile encryption methods towards open, standardized, much tougher algorithms.
Precisely. It's a great example of security having to evolve constantly to meet new threats.
Interesting.
And that need for stronger security, it's not just about keeping data secret. It's also about making sure it hasn't been messed with. Integrity. Which brings us neatly to authenticated encryption, or AED.
AED, okay. Sounds like it's doing 2 jobs at once, like a double layer.
That's a perfect way to put it, yeah. AEAD encrypts the data, keeps it secret, but it also guarantees its authenticity.
So you know it's secret and hasn't been tampered with.
Exactly, like sending a letter that's sealed, but the seal itself is tamper-proof. You need both. And AEAD also handles this thing called associated data.
Associated data, what's that if it's not encrypted? How's that protected?
Good question. Think of it as extra context, stuff that's important but maybe doesn't need to be secret itself, like maybe the header of a network packet or...
The address on that sealed letter.
Perfect analogy. The address isn't secret, but the tamper-proof seal also covers the address, right? So you know that hasn't been changed either. It gets factored into the authentication check.
Okay, got it. So how do we actually do this? Encryption plus authentication.
Well, the dictionary lays out basically 3 main ways it's done. First is the sort of traditional approach. Take a good cipher, like AES, and bolt on a separate good message authentication code, a MACI, like HMAC SHA 256.
Cipher plus AMAC. Seems straightforward.
It can be, but it's also sometimes less efficient and honestly easier to mess up during implementation. Because you have choices.
Yeah.
Encrypt then MA, MAC then encrypt, and they aren't all equally secure.
Ah, okay. Potential pitfalls there. What are the other ways?
The second way is using a standard cipher, but with a special mode of operation designed for AEAD, or maybe combining it with a sort of ad hoc MA.
Examples.
The really big ones you see everywhere are AES-GCM and Chachin-20 Poly 3305. You find those in TLS 1.3, for instance. AES-SIV is another, though it's a bit different, uses MA and encrypt. Chachin-20 Poly 305 is known for being really fast, especially in software.
Okay, and the third way.
The third approach is to build custom two-in-one algorithms, designed from scratch to do both encryption and authentication together, really tightly integrated.
Ah, specialized tools.
Exactly. Things like Acorn and Aegis came out of the Caesar competition. The idea is often better performance and maybe a simpler security analysis because it's all one unit.
Let's dive a bit more into AES-GCM then. That name pops up all the time.
It really does. AES-GCM, that's AES in Gallo counter mode. It's become super dominant. Pretty much replaced separate HMSEs in many places.
How does it work, basically?
Well, it uses counter mode, CTR, for the encryption part. And then for authentication, it uses something called GMAC, Gallo MAC, that generates the tag based on the ciphertext and any associated data.
And the dictionary mentions something about CPUs having a special instruction just for this. PCLMULQDQ.
Yes, that was a big deal. Intel added that instruction around 2010, I think. It massively speeds up the specific math, the carryless multiplication needed for GMA, made AES-GCM way faster in practice.
But it also talks about an Achilles heel. That sounds kind of worrying for something used so much.
It is, yeah. Despite being everywhere, AES-GCM has this critical weakness: nonce reuse.
Nonce. That's the unique number used for each message, right?
Exactly, a number used once. If you accidentally use the same nonce for two different messages with the same key, disaster.
How bad?
Really bad. It can leak the plain text and potentially even let an attacker recover the secret authentication key used in GMA.
Wow. Okay, that is serious. And yet, like you said, it's in TLS, IPsec, SSH, vital stuff.
It is a major caveat. It just means you absolutely have to manage your nonces perfectly. No mistakes allowed. Which, you know, in the real world,
Mistakes happen.
they do. And that's why we have AES-GCM SAV.
SIV, the fix. More resilient version.
You could definitely call it that. The SIV is for synthetic initialization vector. It tackles that nonce reuse problem head on. It cleverly derives the nonce from the message and the associated data using the authentication tag process. So even if you mess up and reuse a nonce input value, the actual nonce used internally is different, so it stays secure. It's called misuse resistance.
That sounds much safer. Built-in protection against that common error.
Exactly. The dictionary also points out it uses a MN encrypt structure, unlike AES-GCM's encrypt than NA. It might not be quite as common yet, maybe a tiny bit slower, but it provides that crucial safety net.
Fascinating trade-offs.
Okay.
Moving from specific algorithms, the dictionary brings up some fundamental ideas like Kirchhoff's principles. I think I've mostly just heard the second one.
That's super common. Auguste Kirchhoff wrote these down back in the 19th century in La Cryptographie Militaire. And yeah, the second principle, security should depend only on the key, not keeping the algorithm secret. That's the famous one.
And it seems totally accepted now, with open source crypto being standard practice.
Absolutely. It's foundational. But he actually listed 6 principles, and they're all pretty insightful even today.
Okay, what are the others? Lay them on us.
Right. So besides number 2, 1, the system should be practically indecipherable. 3, the key must be manageable, easy to remember without notes, easy to change. 4 was about telegraphs, less relevant now.
Okay.
5, the equipment should be portable, usable by one person. And 6, it should be easy to use, not requiring lots of rules or mental strain.
That fifth one, about single-person use. That's really interesting compared to modern stuff, isn't it?
It really is. He was thinking about physical code books or devices. Today we have things like distributed key generation, threshold crypto. The complete opposite goal, needing multiple people.
Yeah, big shift. And the third principle about key management. Wow, that still feels incredibly relevant.
Oh, totally. Getting keys securely distributed, changed, revoked.
Yeah.
It's still one of the hardest parts of practical cryptography. Huge challenge.
Definitely. Okay, let's shift gears again. Let's talk about something much more recent. Blockchain. The dictionary calls its impact on cryptography both a curse and a blessing. Strong words.
They are. And you can kind of see why some might have felt that way initially. Maybe the hype around blockchain sort of overshadowed other crypto research for a while.
Yeah, the whole cryptocurrency buzz.
Right. But the dictionary quickly pivots, and I think rightly so, to the really positive, almost revolutionary impact blockchain has had on cryptography itself.
Okay, so what are the blessings then? What good has it brought?
Well, first, it's just generated a ton of new, really hard, really interesting problems for cryptographers to solve. Stuff way beyond just designing ciphers.
Like what?
Things like, how do you get distributed consensus securely? How do you make these systems scale? How do you provide real anonymity? How do you make different blockchains talk to each other? These are huge crypto challenges.
Right, it pushed the boundaries.
Massively. Second, it meant deploying advanced crypto techniques like zero-knowledge proofs at a massive scale, facing real attackers, real-world constraints, not just theory anymore,
Learning by doing, basically on a global stage.
pretty much. And third, the funding landscape changed. Lots of money flowed into blockchain projects, often bypassing the slower, traditional academic grant systems.
Less bureaucracy, maybe?
Arguably, yeah. And it also brought in this wave of really passionate people, developers learning and building complex crypto stuff, maybe without a formal PhD focus, just getting it done. Now, that also means you have to be careful about rigor sometimes, but the energy is undeniable.
And it specifically mentions things like CDK snarks and bulletproofs for anonymity. Those are big deals in the space.
Huge deals. Sophisticated crypto tools that really found their killer app because of the needs of blockchains.
Okay, now for something completely different. A story that honestly sounds like a spy thriller. Crypto AG, the Swiss
Oh,
company,
yeah. This is an incredible story.
secretly owned by the CIA and German intelligence.
That's the story, yeah. For decades, basically from the 70s up to the mid-90s, this company, based in neutral Switzerland, so everyone trusted them, right?
Right, the neutrality factor.
They sold top-of-the-line encryption gear to governments all over the world.
And the whole time, there was a backdoor.
The dictionary calls it, quote, the greatest backdoor of all time. And it's hard to argue. Governments in the Middle East, Latin America, Africa, they bought this Swiss gear specifically because they didn't trust American vendors.
Oh, the irony.
Exactly. And they were unknowingly sending all their secrets straight to U.S. intelligence via these rigged machines. The NSA even codenamed the operation Minor Nerva.
That is just mind-blowing. How did they do it, technically?
Well, a lot is still classified, obviously, but the dictionary suggests that starting around the mid-60s, their algorithms started using feedback shift registers, those LFSRs again.
Okay.
And the trick, apparently, was that the NSA could influence the choice of certain parameters within those registers. Specific settings were chosen that made the output of the stream cipher. Well, not totally random. It had subtle patterns, short cycles, that allowed decryption if you knew what to look for.
So it wasn't like a simple flaw, it was a deliberately engineered weakness, hidden in plain sight.
That seems to be the case. Just subtly weakening the crypto without making it obviously breakable to the customers, and it worked for decades.
Wow, the whole history, from the Swedish inventor onwards. It's wild. What a cautionary tale about trust and supply chains.
Absolutely. A stark reminder.
Okay, let's pivot back to some core concepts. The dictionary calls the one-way function a cornerstone of modern crypto. Can you break that down simply?
Sure. At its heart, a one-way function is just a mathematical process that's easy to do in one direction, but incredibly hard, computationally infeasible to reverse.
Easy one way, practically impossible the other way.
Exactly. If I give you the output of the function, finding the original input that produced that output, well, good luck. It would take more computing power than exists.
Like trying to unmix paint or unbake a cake.
That's a great way to think about it, yeah. The formal definition is much more precise, of course, involves probabilities and computational complexity.
But the core idea is that irreversibleness.
Right. The difficulty of finding a pre-image, the input given the output.
And these are fundamental for things like hash functions.
Right, absolutely essential. They're the bedrock for so much cryptography, including hash functions, which we should definitely talk about, especially for passwords.
Yes, password hashing. The dictionary makes a point that regular fast hash functions like SHA-256 are not good enough for passwords. Why is that?
The key reason is, well, us humans, we choose terrible passwords, generally. They have low entropy, meaning they're not truly random.
Use birthdays, pet names, password 123.
Exactly. So attackers don't need to try every possible combination of characters. They can just try dictionaries of common passwords, common variations, common substitutions.
And if the hash function is fast,
They can try billions or trillions of guesses per second, especially using GPUs or specialized hardware. If they get a copy of a website's hashed password database, they can crack many of them offline very quickly just by hashing common guesses and comparing.
okay, so fast is bad for passwords. What's the solution?
Specialized password hash functions. These are designed to be deliberately slow, computationally expensive.
Making the attacker's job much harder.
Much harder. They often include parameters to control how slow they are, maybe requiring a certain amount of memory too, which makes them even harder to accelerate with parallel hardware like GPUs.
The dictionary highlights Argon 2 as a particularly good example. What makes it stand out?
Argon 2 won the password hashing competition a few years back. Its big advantage is that it's designed to be deliberately memory hard as well as computationally hard. You can tune how much memory it requires.
Why is memory hardness important?
Because GPUs, which are great for parallel computation, often have limited amounts of fast memory per processing unit. Forcing the hash to use a lot of memory makes it much less efficient to crack passwords using massive GPU arrays. Argon 2 also has clearer parameters for tuning compared to some older ones like PBKDF2, bcrypt, or script.
So it's got a modern recommendation, the gold standard right now.
It's certainly a very strong, widely recommended choice, yeah. For securely hashing passwords or any low-entropy secret, Argon 2 is a top contender.
Well, this has been quite the journey through these crypto tidbits. Really fascinating stuff.
It covers a lot of ground, doesn't it?
It does. We went from, early mobile phone ciphers like A51 through the details of authenticated encryption like AES, GCM, and its SIV fix.
Touched on fundamental ideas like Kirchhoff's principles.
Look at how blockchain has shaken things up, that incredible crypto AG TRIPI story.
And finished with those core building blocks, one-way functions, and password hashing.
Yeah. Hopefully for you listening, you've definitely picked up some new, interesting nuggets from this huge field.
Absolutely. It's a field that underpins so much of our digital world, often in ways we don't even see.
And maybe here's a final thought to leave you with. Think about that constant balancing act in crypto, the tension between making things secure, making them usable, and the potential for misuse. As you go about your digital life, how does understanding even a little bit more about these underlying cryptographic ideas change how you think about your own privacy, about who and what you trust online? What other things that seem simple on the surface might actually hold surprising depth, just like some of the concepts we touched on today?